Uh, Hello and welcome, everyone. I'm so glad you could all join us. My name is Joanna Scharf, and I'm the chair of the Cornish Energy Committee. This is the educational forum organized by the Energy Committee entitled, Where is the Water Damage Actually Coming From? A talk on the mechanics of condensation in homes by Nate Gusakov. I'll introduce Nate in a moment. I first need to review a couple of things. First, it's the policy of the Cornish Energy Committee that we do not endorse any particular contractor or product brand. This event is for educational purposes only. Second, I'm excited to tell you that the second part of this educational series on building science will take place via Zoom on Tuesday, December 2nd, at 7 p.m. It will be a talk by Ethan Cole of Earthshare Construction and Ryan Hareth of GeoBarns entitled Fundamentals of Energy Smart Cost-Conscious Building for Experts and Beginners. Um, they will be defining basic terms such as dew point, air exchanges per hour, vapor barrier, air barrier, and they'll discuss best practices for building envelope and wall construction and the pros and cons of various types of insulation, among other things. So I hope you will all join us for that talk as well. Now, I am thrilled to introduce Nate Gusakov. Nate is a building envelope expert and the owner of Green Mountain Enclosure Consulting. He performs a variety of services, including residential and commercial whole building airtightness testing, qualitative thermal imaging, envelope failure forensics, existing building envelope assessments, and building science teaching and presentations. Nate also sits on the board of directors for the Vermont Green Building Network and is a voting member of ASTM Technical Committee E06, which addresses performance of buildings. Nate is going to talk he's got a lot to cover, so his talk will go for about an hour. And I ask that you please hold your questions until he has finished his presentation. We hope to have about 30 minutes for questions afterwards. And when we get to the question and answer period, we ask that you use the raise hand feature on Zoom instead of the chat box. And you'll find that button at the bottom of your screen under the image of a heart, and it's labeled react or reactions. I hope you will find the information presented here as fascinating as I do, and I want to thank Nate Gusakov for being here. We are tremendously grateful that you are giving us your time today and for sharing your expertise with us. So I'm going to turn it over to Nate now.
All right. Thanks, Joanna. Well, hey all, glad to be here. Um, let's see, one quick thing. I may whip through my so-called hour of material in 45 minutes just because sometimes I do that. And so know that as the questions come, I will be happy to sort of dive back into the slides and really dig into them. I consider the question and answer period equally, if not more valuable than as compared to just me yammering away at you. Um, that being said, I'm going to share my screen here in a moment, and we'll go to PowerPoint and we'll get right into it. Let's see. Okay, do the things. Oops. Okay, everybody can see that. It's working all right. Trust that it is.
Yes, yes.
Yeah, great. Thanks, Joanna. Okay, basically almost disregard the first two words of the subtitle there until the very end of this. We're really going to focus on the mechanics of condensation because that physical exchange is at the heart of a lot of building science and a lot of building science concerns. We've Joanna did a great intro. I worked with Connor and Buck as a local design and build residential construction firm out of Bristol, Vermont, where I'm from, through high school and long afterward. And a quick note on that, The demolition that we did, the taking apart of existing buildings, anytime I renovated an old Vermont farmhouse, I've come to realize that was absolutely hyper valuable frontline forensic experience about what happens inside a building assembly over years in Vermont, or in the Northeast, I should say. Anyway, yeah, I did a whole bunch more stuff. It's all been building science related. We don't need to go. Joanna did a great job of going over kind of where I'm coming from. I did get my actual bachelor's degree in sustainable agriculture. Still keep a horse and, chickens and a good big garden, all that good stuff. All the rest is just blah blah blah, acronyms related to building science. So there's the ASTM stuff, the Vermont Green Building Network, Air Barrier Association of America. Yep, there's such a thing. Backcountry Hunters and Anglers, great association, totally unrelated to building science, but check them out. Very devoted to public land access all across the country. Okay, into the good stuff. Um, okay, so why do we care about any of this in the first place? Well, we like our buildings to be durable and safe and not get damaged by living. So what are the things that harm a building? UV radiation, a little bit. You'll have to bear with all my animations. You'll see that I love my PowerPoint animations. Heat, sure, it can, especially if it gets too hot. You can loosen up glues, blah, 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 but not really. These things pale in comparison to this one. And yes, it continues dropping in ad nauseum because that's how water works and physics never sleeps. And because water is really the thing that is the danger to buildings. Okay, well, how wet is too wet? Um, so generally speaking, at 70 degrees Fahrenheit, now that's really important. The cooler things get, the slower all of this happens. The hotter it gets, the faster it happens to a certain point until you get too hot for mold to grow, but we're not worried about those conditions. So normally speaking, if there's liquid water on a surface, on a rafter, on a piece of sheathing, whatever it is, it's going to have to dry within 24 to 48 hours or you're going to start to get spotting. And if it keeps going, that spotting is going to turn into real surface mold. So fairly quick. Now, that's liquid water. That's literal. You can see it, touch it. There's liquid on the surface of a thing. Wood moisture content is a slightly different thing. It's sort of how much is intracellularly and intercellularly absorbed by the matrix of the material it's on. We use wood moisture content, or the WME there is wood moisture equivalent. Um, they're slightly different, but they're basically the same idea for non-wood materials. So an average house, the framing is 8 to 12-ish% seasonally in the Northeast. If you take a wood moisture meter and stick the pins in there and it does a little electrical measurement, that varies, but that's generally where we're at, and that's a fairly safe range. If you get up into the 16 to 19% for 5 days and longer at this 70 degrees, you're going to start to get surface mold, even if you don't see that liquid water on the top, right? There's enough moisture in the substrate of the wood that it's going to grow these surface molds. The things that are easily, the spores are easily inoculated via the air. They're landing on the surface of that wood and it's plenty moist and it's like, oh, cool, I've got continuous water. Wood moisture content of 20+%, like 24, 25, 26 for longer. And then you're getting into a whole nother class of growth. And that's the stuff that grows down into the substrate and eats it, not just stains it and puts nasty spores on the surface. And so I know that these numbers on their own don't necessarily mean much, but it does sort of tell you like, this is what we're talking about when we're talking about damage factors, danger, things that are going to cause trouble either to our health or to the durability of the building. Okay, circle the must dry part. That's key because if it does dry fairly quickly, wood can get wet a lot and it can get wet for, over, I mean, think of some of the old cathedrals in Europe. They're hundreds and hundreds and hundreds of years old, 700, 800 years old. The wood is fine, and I guarantee you it's gotten wet a time or few. one way or another over the years, but it never stayed that way too long. And that is really, really critical. And one of the reasons I bring that up is that I think on a cold winter night in New England, 80%, if not more, of the buildings probably have some condensation on the bottom of the roof deck somewhere, or like somewhere in the assembly, but it dries back out. It only happens under sort of worst case scenario conditions when it's really, really, really cold. And I think there's a lot more sort of wetting and drying than we give credit for. And so just that concept of wood being able to dry back out, and then by extension, we'll get into it more, assemblies, wall assemblies, ceiling assemblies, etc., being able to dry is absolutely critical to all of this. Like, it's great to try to never let something get wet, and we are pretty good at it. But if things do get wet, when they can dry, that's key. Okay. And you'll see there will be these recurring themes, if I've done this well, that kind of keep popping up. Let's just go into just sort of an overview of water just for a minute, because it's kind of unlike any other substance that we have here on Earth. It's amazing. Well, there's your H2O, there's this nice little molecule thing. Ice is less dense than liquid water. Water expands when it freezes. We all know this. Here's a great little way to look at it. Here's the gas, here's the liquid, here's the ice. It's all nicely arranged. That is a very, from a building science point of view, fairly problematic property of water, because when you get small bits of water inside tiny bits of building assemblies that are then allowed to freeze, that water exerts crazy pressure as it expands, and it can do things like pop bricks open and, et cetera, et cetera. Um, Liquid water flows downhill, except when it doesn't. Okay, fair enough. Things like capillary wicking, hydrostatic pressure, we'll go into those a little bit more later, but we're not too much. Those two in particular, capillary wicking and hydrostatic pressure, have a lot to do with the amount of moisture that is going to come up from the ground into a building if not properly stopped. And we are absolutely going to talk more about that later. But just bear that in mind, that for the most part, we deal with liquid water, bulk water, rainwater, etc., by shedding it away, knowing that it comes down from above and we can direct it downward, and gravity will do most of the work for us, as long as we mind a couple of exceptions. Number three is the one we're really interested in here: water vapor. It's invisible. It is held in solution, in chemical solution in the air. It's up here. And, great. Let's circle that. Also, to be clear, steam, visible steam, when you see steam, that's not water vapor. Those are little micro droplets of liquid water. Because they are visible by sort of definition, they're too big to be vapor. They're no longer in chemical solution. They're actually just suspended in the air as little micro droplets. And that's what steam is. When you take an exhale on a cold winter day and you see your breath, the part you see is technically liquid water. As soon as it disappears, that's the water didn't go away. The H2O molecules did not like vanish from the existence, but it became truly in solution in the air. It became water vapor. And that's important to make that distinction. And I remember that was a bit of an aha moment for me when I really realized, like, oh, you can't ever see water vapor. How are we doing on time? Oh, just fine. Yep. Okay, miraculous stuff. It is. And we're made of it, and the earth is mostly made of it. It's kind of funky. Okay, here we go. Where is the water coming from? So this is the beginning of the real intro to the mechanics of condensation. Rule number one: warmer air can hold more water vapor in solution than cooler air. This is a universal law. Discuss amongst yourselves. Which is to say, there's no discussion on this. It just is, that's like, we have to accept that. When air is warmer, it can hold more water vapor in solution, invisibly inside its bulk, than cooler air can. Okay. Well, what does that mean? So we get this thing called condensation when this warmer, moist air meets a cold enough surface. Now, there's more that goes on. It's not that the air hits the surface exactly. The air actually cools down because the surface draws heat from the air. We're about to get into that. That just that sentence alone, this condensation occurs when warm or moist air meets a cold enough surface. I literally in my work almost on a daily basis just repeat that as a mantra as I'm trying to figure out what's going on in buildings because the physics are always that simple. It's just that there are, 1.4 million microclimates within any house, and the interactions go all different ways, and there's lots of different factors, but the basics. How does water just appear? Well, it's when warmer, moist air meets a cold enough surface. How cold? Below its dew point. They all yelled excitedly. I could hear you guys. I heard it. There's that magic word, dew point, and that is exactly what it means. It means the temperature for any given mass of air and the conditions that it's in. When the temperature gets low enough that that air can no longer hold the water that has been in solution, therefore that water must find a way out of the air and it finds a surface on which to condense, i.e. dew. Um, when we see clouds, generally, well, yeah, clouds are exactly that. As you know, steam, visible water is not vapor, right? And so clouds are not actually vapor. They are where the vapor can no longer be held in solution. The air gets cold enough, and what happens is the vapor finds the nearest condensing surface, and in the atmosphere, that's usually microparticles, little micro dust or whatever, something to glom onto, and then another molecule does, and another as they drop out of the solution. Then all of a sudden they become visible. You get enough of those, and they get big enough, they clump together enough, they get really heavy, and they start falling. And then what do you know? Rain. Okay. Um, yeah, and this on the bottom here. So the condensed moisture comes from the warmer air, not from or through the cold surface itself. And that, for many may be like, yeah, duh. For me, it took a long time for me to get that. Just because, for example, when I look at a window pane that has condensation on the inside, it just feels like that water came in with the cold, you know? And it's not. It's water from this nice warm inside that gets too close to that cold surface and can no longer be held in solution. So we're going to really double down on this exact same thing. And yes, it's repetitive, but again, like that's the whole point of me wanting to focus this entire talk on this mechanism, because once this mechanism is really understood, it applies in so many of the questions that I get asked. I just repeat that mantra and then apply the mechanism of condensation, and that's where the answer is. So, okay, we're going to look at it again. You bring a cold can of something out on a nice warm summer day, and immediately it gets all sweaty. And so there's the can. Here's the air as it is. We've got temp, it's 90 degrees Fahrenheit. Relative humidity is 70%. Now, this cloud, it doesn't represent an air mass exactly. It's a figurative representation of the ability of a certain amount of air to hold water. And these droplets represent molecules held in suspension, right? So that's vapor. You can't see it. As we get closer to the can, because it's cold, it's drawing heat out of the air from it. It's cooling down the air around it. The air gets a little bit colder. It's 80 now, as you know, who knows, we're what, a quarter inch from the can. Relative humidity is going up. It's the same amount of water. Notice there are these three droplets. It's the same grains of water as the actual sort of measurement of water held in solution in the air. It's grains. It's literally a weight. And so it's the same amount of water, but the capacity of the air to hold that exact same amount of water is quite a bit less because it's cooler air. And so it's getting closer to where the water is kind of filling up the air, as it were, the air's capacity. Now we get really close to the can. Maybe it gets down to 70 degrees right in that last, whatever, 64th of an inch. All of a sudden, that same amount of water that was held in the air right there, it's too cold. It can't be held in solution because of this incontrovertible universal law. And so it drops out of solution. It starts flocculating with itself and with whatever nearest condensing surface there is. Well, there's a nice, really cold aluminum surface right there. Voila. And as soon as one droplet forms, the reaction keeps going until that can no longer has enough cold, or I should say, has absorbed enough heat from the atmosphere that it's come up to the same temperature, at which point all of those droplets will then slowly reabsorb back into the air, which is now warm enough around them that it can reabsorb them and it evaporates. It turns back into vapor. Um, yeah, and this slide is kind of it. All right. I mean, whoops, I didn't mean to do that. Um, I think, you know what? Because I'm leading the show, I'm gonna do this and nope, not that. I'd love to just open it up for questions. Um, I think now would be a decent time because the next here we're gonna stop share. The next portion is taking that mechanism and starting to apply it to buildings. And so I think it's a great time for anybody to go ahead and if you have any questions, raise your hand or just unmute yourself. But I guess raise your hand and I'll do my best to recognize. And if not, I'll just keep blabbering away.
Again, if you want to use the raise hand feature, go to the bottom of the screen with your cursor and you'll see a little heart and the word react. And oh,
Yep,
there's
Richard,
one.
got it.
All right, so it seems like a good opportunity to see if anybody can answer this question I've had for ever since I built my house. Is there any way to prevent condensation on windows when it gets below zero?
Ah, very good question. So the whole driver of condensation on windows is there are equations for this very thing, like where dew point occurs, what's the relative humidity inside and the temperature and what's the surface. And the colder it gets, the harder it is to avoid that because you keep dropping that surface temp and the dew point, just keeps following with it. The colder it is outside. Triple pane windows are, to me, yeah, I got to be careful. There's so many tangents. Let me back up a little bit. So a single pane window, it's got an R value. Let's call it R2, maybe a little less than that. Sure. Double pane, modern insulated two pane argon low E window, R three and a half, four, probably, pushing four. A nice triple pane window, R5, maybe six. I mean, sure, some might be claiming up to seven or eight, which would be like off the charts. That's still a third the R value of the R25 wall that's right next to it. So even triple pane windows, when you're looking at just actual heat loss, like BTUs, yes, they help. They're not necessarily like, wow, those cut the heating bill. But what they do, and this is, I think, the more valuable factor for triple pane, is that third pane inside is a bit warmer than even that second pane, and so you're much less likely to hit dew point. They can get colder and colder and colder outside, and that third pane is still going to be that much warmer. Um, so to get back to the sort of the heart of the question, like there are a few ways to avoid it. One, you somehow make the interior surface warmer. And so either it's yet another pane of glass, you can do the plastic film on the inside. I know some people like
Mhm.
it, some people don't, but it actually works beautifully to avoid condensation if it's done well. Um, there are even like in Europe, I've seen you can buy these little heating strips they stick onto the bottom of the pane, literally onto the
Yeah.
glass, like down at the bottom
Right.
where it always condenses, and you plug it into the wall
Huh.
and it just goes bzzz and emits a nice little bit of heat and it warms up that pane of
Interesting.
glass. Voila, no more condensation.
Hmm.
Um, Throw energy at it, right? Like you can certainly do it that way.
Yeah.
I will say that air movement also disrupts condensation because, especially in the beginning stages of condensation, because things don't have a time to settle and to coagulate and to form. And so moving air around, even like a ceiling fan, or if you wanted to go crazy with it, literally having a fan blowing on the worst offending window, is it going to totally solve the problem? No, and it's actually going to bring the cold into the house more efficiently, but it will slightly reduce the condensation on the pane. So yeah, all the above. And with good old sort of standard two-pane windows that many houses have from the last 30 years or so, yeah, basically when it's 10 degrees or colder,
Yeah.
and depending on where you keep the house, the other answer is you can drop the relative humidity.
Right.
But when we get, usually in the winter, we're at about 40 to 50%, 40 to 60% ish. And when we get below 30% relative humidity, our bodies start suffering. Uh,
Hmm.
we just, our skin gets dry. We'll start getting nosebleeds. Like we don't function well when it's that dry. It's great for the windows. It's great to reduce condensation, but we just can't really function. So yeah, that's totally a thing. Yep.
Okay, thanks.
Yep. Anybody else at the moment? Oop, I see one other. Where is it? Kate, yeah, go ahead.
I'm going to try to ask, I hope a simple question regarding condensation. You're insulating a garage attached to a heated home. Does the paper barrier, where does it go? Do you have it outside, on the outside where you look at it when you're parking the car, or do you have the pink? Because I'm trying to follow what you're saying about condensation.
Hmm. Yeah, you're on the right track with it. So yeah, before getting off on all the tangents that I want to, let me try to just answer the question. If in general you want the paper, which is to say the quote unquote vapor barrier, and massive asterisk on that term, but for now we're just going to think of it that way, the paper on the warm side, because on the warm side is where the air is going to be holding more moisture, and you want to stop that moisture from getting past the insulation to where things are cold. That's generally the idea. Garages can be a little bit funny because it's like, well, is the garage, like, is it going to have a lot of runoff and snow melt and car stuff in it? But if the house is to be the warm part and the garage is to be the cold part, then in theory, the paper would go on the house side. Is that?
Okay, what about the outside wall of the garage?
I see. Um, and is the garage going to be heated and part of the warm airspace of the house?
The garage is unheated.
Unheated. Got it. I mean, generally speaking, I think you can just assume that the paper goes on the inside, the warm side.
Okay,
And in this case, it sort of won't matter as much because the garage, yeah, well, for a few reasons, and it'll segue well into what we're going to get into, which is moisture sources. Like, in order for there to be the moisture in that warmer inside air, there's got to be a source for it. And so if the garage isn't necessarily connected to like bathing and cooking and breathing and etc., it may not be that much of an issue. Also, if the garage is unheated, it's not going to be that much warmer than the outside. And so there's not going to be that much of a temperature difference. But generally speaking, and Ethan or anybody else who's, more in the world of actually working with stuff with their hands can speak up if I'm totally remembering it wrong. But I think the paper goes on the inside, on the what you would call the warm side of the assembly. Where I see a thumbs up. Awesome. Good.
thank you so much.
Absolutely. All right. Anybody else? Keep on rolling here. Cool. Okay. Back to this, to this, to this. Okay, so we are all so good at this part now. So exactly as I was saying, kind of, okay, so now that we've got the basic mechanics, quote unquote, of condensation under our belts, like how does this apply to buildings? And I'm sort of shifting gears. I'm still going to keep it within the mechanics of condensation realm, but this is starting to get into, especially with renovations, which is often where these questions are coming up. What do you do? What are the things to pay attention to? And the mechanics of condensation will keep popping up as the reason for, what I'm suggesting. So anyway, so where is the water coming from, right? Like, how does it get into that warm air in the building in the first place? Well, dirt floors are the worst of the worst. Um, there is so much moisture that comes up from the ground, even if it's a dry summer, even if it's like there's always ground moisture coming up through. Even if, for example, and I've had people ask, it's a really good question, like, well, what if the house has really wide overhangs or even what if there's like an underground, quote unquote, underground roof, which is like a shedding layer that goes out from the house, 4 feet underground, and any water is shed out 4 feet away from the building. It's still gonna the ground is homogeneous with the earth. Like, it's too big. We can't dry it out. So dirt floors, and over here's a classic sort of dirt floor crawl space, just breathing up. Here is in the center, hopefully you can see my cursor, a cinder block wall that's set right down on, I think, more cinder blocks that are right on dirt, and it's just been wicking. Here's that capillary action, moving water uphill against gravity, just wicking up and bringing salt with it, and da 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 da. And same deal over here on this post. It's set on a piece of wood that's set on a dirt floor, and the water is just shooting up through. Okay, what else? Humans bathing and cooking and simply existing. Darn it. 2 to 4 pints a day just to breathe and evaporate off our skin. Like, no kidding. Yep. Not to mention bathing, not to mention cooking. Cooking is a huge one. You get 3 pots of water on the stove boiling away, and like, that's a lot of water vapor going up. Showering, big hot shower for 15 minutes. I mean, the amount of steam generated is huge. Pretty quickly, you don't have to connect too many dots here to see the very important connection between proper ventilation, proper exhausting of moisture, and health and durability of building assemblies. And then bulk water issues as well. Roof leaks, splashback, improper drainage, like, absolutely. If and when those are gaining direct access into a building via a roof leak or whatever, or like a splashback that just hasn't been waterproofed, that's a huge point source, and it's sort of directly applying the water to the building. We're pretty good at taking care of bulk water because it messes things up really quickly. We haven't been great at dealing with condensation, although we're getting better and better at it, because it takes a little bit longer to express, and it takes a bunch of sort of worst case scenarios in a row, or it takes a while to see the damage. Although in modern quote unquote high performance homes, where it's a really airtight building, it can happen quick. 2 to 3 years, and all of a sudden there can be mold or rot showing and whatnot, just because and that's, there's a slide that I guess I should have in here, which I don't, which is about that very thing, like, sort of the brief history of building science, as it were. And like, in a nutshell, it goes like this: like, for 200 years, our buildings were mostly fine as long as the roof didn't leak. We didn't have too much condensation issue. We didn't have too much air quality issue. Dirt floors didn't seem to be a problem, and that's because they were 30 to 50 times as leaky as a modern high performance home in terms of air leakage. And so with all that air leakage went all the moisture and also all the heat, but that was just the way it was, right? Takes 12 to 17 quarts to heat a farmhouse in a winter. Basically in the late 70s, the oil crisis happened. We started trying to save heat. We started insulating things. It did save heat, but what it also did is stop that heat from getting to the surfaces that are behind it, like the backside of sheathing and the underside of roof decks. And so suddenly they're really cold, but the warm, moist air from inside can still get across the insulation. Actually, you know what? I think this is gonna work out. I'm realizing that I'm describing my next slide. So yeah, I'll just continue with that briefly. Okay, so we did that. Well, then we're like, oh no, we need to stop the air as well because the air is carrying all this moisture to the cold places. So we started putting plastic on everything and we stopped the air, but we also stopped the moisture from getting out at all. And so the moisture is just building up and building up in the house. And then where it does have a leak through the plastic, it just carries to a cold surface, and we had real trouble. So then we started saying, wait, well, we do need to exhaust air out so we can get the moisture out. Okay, let's put fans in, but boy, then we're just blowing a lot of heat out. And also, where's the new fresh air coming from? Well, maybe we should make like a balanced exhaust system so that the same amount goes out as comes in through the system, and maybe we could filter it, and maybe we could even have it exchange a little bit of heat. And so we invented ERVs and HRVs, and like here we are in the realm of modern building science, still building very airtight buildings and hopefully getting the ventilation right. And certainly, and I'll come back around to this when we're talking about renovating and wanting to weatherize and wanting to insulate and make more airtight, the moisture sources have to be addressed first. Otherwise, you just start trapping moisture in places you don't want, and getting really long-term condensation buildup. So, okay, here's a little box that we're going to live in, but the water gets on it, so we put a roof on it to shed the water. Okay, good. Also, we've been doing this for a while, and boy, that bulk water is a thing. So let's try to site the house well, and maybe those little drainage, drainage tiles underneath. This is all bulk water stuff, and like we deal with that whether we're warm or cold. We deal with bulk water in the in the rainforest climates as well. Like we don't like getting rained on in our homes. Okay, fair enough. Now let's bring it up to the cold Northeast. All of a sudden, brr, it's 10 degrees outside. Okay, well, we're going to heat that space because we want to stay warm. So now we have warm air, a big, huge pocket of warm air in the midst of all this cold. And we're going to lose heat. Okay, so we're going to insulate. We're going to put something across, especially in the attic, because boy, that heat rises, right? Cold air pushes heat upward. Pushes warmer air upward, I should say. Okay, so there's this funky attic space in here, which is like it's still cold, but it's sort of blocked. It's got things here, and we have the moisture and this warm, moist air still making its way through the insulation, and getting into this space, and it'll condense like crazy. So we've been really good over the years. Like how many old farmhouses had attic vents? Even back then, we understood like, cool, let the air out, let the moisture out. So there'd be a gable vent up here or a soffit and a roof vent. But for now, we're trying to solve the problems as we go. So we're saying, okay, well, we've got all this warm, moist air escaping up into here. Okay, whoops, I guess I had my animations wrong. So yeah, here's venting. This is how we address this problem and how we addressed it for a long time and how it still works beautifully. Put a soffit vent in down here, put a ridge vent in up here. Any of this warm moisture that comes up into the cold space, instead of being trapped and condensing, just gets to be whisked away by this nice current of air. Or there could be just gable vents, same idea. As we get into wanting to be more and more high performance and saying like, well, let's just try to stop the air. Or, shoot. Okay. Yeah. My apologies on the animations. Okay. So another thing we can then do is put some sort of a vapor barrier on the ground, put some sort of a non-dirt floored basement, build a plastic bathtub, essentially, as it were, inside of an existing dirt floored basement. This is all in service of cutting down moisture loads on the building. So if we can get something vapor impermeable there, it's going to greatly reduce the amount of vapor that's getting up into here, before we even do anything up here. Just start to cut down on the moisture load. And then the sort of next step is, well, let's build a really airtight building and stop the vapor and moisture from ever even getting out of the warm space. Excellent in theory, great ambition, and many very good builders achieve a pretty bomber version of this, but not all the time. And so I've got there's still a little bit of moisture going through. So especially like I am constantly advocating for vented roof assemblies. And this is not to sort of turn it into a tangent, but this is a very pertinent and common spot where all of what we just went through, the mechanics of condensation, really come into play and really apply. And it's always going to be a problem if a roof is unvented, and it's always going to be a really good solution if it is vented, because that moisture just never has a chance to build up and it's able to whisk away. Look at that. Emphasize that venting. Okay, so just to get back around to, yeah, good. Given all of that, and I know I'm sort of reaching for connections here, but I wanted to try to encapsulate into some, like, here are some things to remember, given everything we just talked about in terms of the mechanics of condensation. So when renovating, step one, minimize sources of moisture. So like if there's a dirt floor, got to deal with that before you deal with anything else. That's sort of the simplest right there way to explain it. That's exactly it. Minimize sources of moisture. Step two, ensure adequate ventilation. So think about where is fresh air coming from, and where is exhaust air going. And if you have, if you're renovating and you don't know how leaky is the place, have a blower door test done. You can quantify it. You can get a sense of like, boy, we could cut the air leakage in half and still have adequate ventilation. Or you might find out that, boy, even if we only get 30% better, we're going to be tight enough that we might not have adequate ventilation. So just be aware of it before you even start thinking about other envelope stuff. Minimize moisture sources, think about ventilation. Step three, pardon me, a little bit of seltzer here. Encourage assembly dryability. And so that now should mean a little bit more than it did, hopefully, before I started talking at you, which is to say, don't build a wall that has plastic on both sides, and so it can never dry to one direction, right? And it really, in some ways, you don't need to think it out more than that. I mean, obviously there's 1,800 ramifications and different products, and there's Intello this and Siga that and permeability rates and like perm ratings and all this stuff. Like, yes, but the basic idea is make sure there's a drying pathway in both directions from wherever the air stops. And that's the overarching thing to remember. And then step four, finally, here we are at quote unquote weatherization, enhancing insulation and airtightness, which is sort of where everybody often starts. And I'm really saying like, whoop, sure, that's the goal, but don't even start it until you've thought about these other three things. I think that's all I got. So let me get out of here and feel free to raise your hands with questions.
Thank you so much, Nate. That is so helpful to me. All right, you have a question.
I see it. H.E. Platt, please go ahead.
Make sure you unmute yourself.
Yeah, go ahead.
We can't hear you.
No sound coming through. I see that you're not muted, so that's correct, but maybe the microphone's not on or something like
Can
that.
you hear me?
Yes.
Oh, there you are.
Okay. Is it counterproductive to have both ridge vents and gable vents?
Ooh, excellent question. I have a snap answer, but I'm thinking carefully before I snap answer. No. And for anyone else in the audience who may have addendums to that, feel free to chime in. But no, I don't think it's ever going to be counterproductive to have too much ventilation. Essentially, that space above the insulation, it ought to be as cold as the outside air, and as it ought to be free outside air. Now, we can't exactly do that because we need to protect the insulation from wind and from rain, et cetera. So yeah, I think, there's a little bit of concern in wildfire climates these days. Actually, there's some of the building science gurus are saying don't vent your roofs at all costs, even in cold climates, because in wildfire spark storms, the roof vents draw embers in and then they burn the house from inside. And it's like this crazy singular problem that is significant enough that it's sort of changing building practices. Here in the Northeast, not so much a concern. So no. There are a couple of rules of thumb. I think it's I should get it right. You can look it up. It's like 1.5 square feet of free venting area per 300 square feet of attic, or maybe it's 3 per 150. It's something along those lines. And generally speaking, like normal soffit and ridge vents systems have about that exact ratio. And if you look at just gable vent systems, they'll also have about that exact ratio. The only thing I will mention, like sort of how could you mess up venting an attic or venting a roof? If you're just doing gable vents, they need to be fairly high on the peak. If they get too far down, you'll actually get moisture trapped above them. And that's sort of like the only caveat about venting. So long answer, but generally speaking, nope, it wouldn't be counterproductive.
Great, thank you.
Yep. Let's see, Deborah Munson. Yeah, go ahead.
Hi, yeah, I actually had sort of the same question. My builder was well, let me back up. My house is from the 80s and my ridge deteriorated, so I just had a new ridge cap put on. And my builder went ahead and put a ridge vent on when my original builder did not put one. I just had gable vents. And so my roofer was very insistent on wanting to close up the gable vents because now, that I was supposed to have just a ridge vent. But I didn't do it. I still have, both there. So I was a little concerned as to his concern, but
Yeah, good instinct to not let him do it. I mean, if it would work to switch it over to a ridge vent system, but the absolutely critical component of that is it has to have soffit vents down at below. So the gable vent, the two triangles in the peak, as it were, that works essentially by sending air across the top of the ridge from gable to gable, or maybe up into the center and then just out both gables. Whereas the soffit and ridge vents work very differently. The air current comes from the eaves at the underside of the eaves up through the soffit vents, and it needs to be able to bypass the insulation layer. And so this is key. And so this is where you get into having, like, you'll see that prop vent stuff, it's called, these sort of venting channels. And that carries that cold, fresh soffit vent air up past and then up along the underside of the rafters and underside of the decking in the rafter bays, and then it goes out the top. So it's a different direction of air movement. So the ridge vent alone, without introducing soffit vents and making sure that they feed to it directly, would have been troublesome. So if that's what they were trying to do, then great call, having them keep the gable vents in.
well, there is a little twist to that. I do actually have the soffit vents that have the cardboard channel things on the underside of the roof,
Uh-huh.
but they only go up to above my layer of blown in insulation.
Yep.
And then they go to the open part of the
Yep.
the
Okay,
roof.
cool. And that's exactly correct. They just need to carry up above the insulation layer, and then that's actually better that they just dump into the air above that.
Right, right.
Yep.
Okay.
So yeah, it would have been okay, I think, to do just the ridge, but again, I don't think there's any harm done by leaving the
Leaving
gable
it.
vents in.
Okay,
Yep.
thanks.
Nate, sorry, Richard, if you can hold off. There's someone who's had a question in the chat, if you don't mind me reading that.
Not at all, please. Yeah, go ahead.
It's from Thomas Griggs.
Yep.
If I closed cell spray foam the bottom of roof sheathing between house rafters to R60, Do I need to have ventilated space between the top of the foam and bottom of the roof deck? If so, what is the best way to do this? Would there be any reason to use a variable perm vapor control layer between sheetrock ceiling and foam?
Oh man, that is all of it in one question. That is spot on for, yep, holy moly. Okay, so it has been common practice to do that very thing, closed cell spray foam, just on an existing roof, right against the decking, in between the rafters, and just call it good. The reason that that is in theory okay is that the closed cell spray foam has, it is by definition, sort of by its makeup, it's vapor impermeable. And so you could think of it as, a thousand layers of plastic all sandwiched together, like all the way on the furthest inside face of the insulation, the very warmest side of it, the vapor stops and it no longer gets through. And so in theory, that would be the way to do an unvented roof safely, is you, like I said earlier, you never let any of that moisture. And actually I'm going to get back to, I was hoping I'd be able to do this. I'm going to reshare, because this question is huge, and it's really pertinent, and it's right in the middle of a lot of conversations that I'm having lately. Okay, so we're going to go back here. Okay, I'll just leave it here. We'll do it like this. So essentially, like, let's say we've got this situation, and one thing that's a little bit hard to explain, but oops, the way that is being talked about doing it, like, you're essentially just moving this whole insulation layer right up against the roof like that, right? You still potentially have this liminal space potentially on the other side of it. The idea is that if you put this spray foam here, the air cannot get past it. The moisture cannot get past it. It always stays in the warm air where it's able to stay in solution. No problem. The issue has been that when spray foam gets installed, especially between rafters, it forms this really nice, like, monolithic plastic block. It's in the shape of the rafter bay, right? That is very rigid, and very stable, and it's also very tough. And the wood and the frame and the structure around it are wood. Yeah, it's made of wood. It's old. It's a little bit movable. It expands and contracts a lot. And so what can happen is it'll actually pop away. And so this block of spray foam cracks away. It's still sitting there, but there's just a little leak, just a 16th of an inch or whatever between it and the rafter. And or there are little places that for whatever reason it just wasn't perfect and it wasn't continuous. And so the issue here then is that you've done a really good job of keeping all the moisture in, but where it can get out, it's going to immediately find a very cold surface but have no way to get away from it. So it has been done a lot, and generally speaking, it works fine, especially with a good spray foam installer. It can be troublesome if there are these little leaks somewhere, because the moisture drive through them is going to be constant. And as you're asking about, like, in this quote unquote traditional way to do it, there's, once it gets to the underside of that roof deck, there's no way to get out. It just has to soak into the wood essentially and start causing trouble. So what I have been seeing more and more, and literally this is only in the last year, or even I would say like last 6 months, is that folks are doing, vaulted ceilings, insulated ceilings with spray foam in the rafter bays, and then also building a vent channel above that. And that vent channel, it's arguable exactly how deep it needs to be. An inch would be plenty. It's often easy to just sort of frame something out of 2x4s on the flat. And so you get an 1.5 inch channel. That's absolutely plenty. And the key, regardless, there are a lot of different ways to build it, but the key is that if and when moisture gets up past the top side of that spray foam, out beyond the insulation into whatever's cold outside, it then has a free path up and out. And so there has to be essentially a soffit vent, as it were, somewhere down here. And so there are varying ways to do that. And the short answer, like, yes, I highly recommend it. It's not exactly simple. It's a bit of a second build, right? Or it's at least a whole nother step. But the degree of safety that it offers is almost 100%. Like if there's a good venting system above everything, as with all these old farmhouses that had dirt floors and who knows what kind of moisture loads, it didn't matter because the attics were really well vented. And so it was fine. So I do think it's worth it. Essentially, there are a couple ways to think about doing it. I've literally seen where like the whole thing gets, it gets spray foamed, and then holes are cut or like routed out of the decking or the roof sheathing, like these sort of ventilation holes, and then maybe covered with a screen. And then sleepers are laid on top of that decking, 2 bys on the flat, so you have an inch and a half, and then another deck or a roof, if you have metal roofing that doesn't need a deck under it. But essentially, you sort of deck the roof twice. Um,
Hmm.
there are ways to try to go around that, but especially if you're dealing with an existing building, yeah, basically what you're going to do is run sleepers down on the top of the existing decking and then put another plywood or board deck and then roof over that and have a ridge vent at the top and some sort of soffit openings at the bottom. Um, the other question was about, yeah, putting like a vapor, a membrane or something, and speak up here. Let me stop sharing it back
Yeah,
to.
can you hear me, Nate?
Yes, yeah, go
This is
ahead.
Tom. Thanks for answering that. Yeah, I was just wondering, I was fearing that very thing you mentioned about the monolithic block of foam potentially parting slightly from the rafters and vapor getting up in there. So would an Intello-like or a VaporWise type variable permeability vapor control layer solve any of that? Just between the sheetrock and the rafters,
Right. I
or
mean,
not?
it's sort of it's essentially doing the same thing as the inside surface of the closed cell spray foam, in as much as you can get any layer that is going to stop air from leaking past the spray foam. Yes. In this case, the vapor permeability doesn't really. That's sort of a whole nother conversation. I mean, the reason for vapor permeability in all of these membranes is for one reason and one reason only, and that is if things get too wet because something went wrong, it can then dry back out in
Mhm.
the original direction to the room.
Yeah,
Mm. Okay. So in this case, what you essentially would need, the thing that would help eliminate the risk with the cracking and whatnot is some other air barrier. It's the vapor we want to be stopping, but just think about it as stopping air, because if you stop air, you've done a pretty good job of stopping vapor. Like we can get into how much actual water vapor will move across a permeable layer. um, the it's been pretty well shown, and there's some great like simple slides about this, that the amount that diffuses across a membrane is just not worth worrying about compared to the amount of vapor that is carried by an air leak, a convective air transport leak. And so in this case, the critical thing would be, yeah, can you put some sort of other layer under the spray foam that crosses where the spray foam meets the wood, right?
yeah,
And there are a ton of ways to do that. One great way is to, if you are able to, is to extend the spray foam all the way around underneath all the rafters. And so every bit of wood is fully encapsulated. So it goes like up into the bay, and it doesn't need to be full depth all the way across the bay because that may be overkill, but it comes down the side of the rafter, over the bottom of the rafter, back up again. And so that way it's actually quite a bit more resistant to that concept of kind of cracking. Um, and it's easier to see in that case that it's good and continuous. It still doesn't eliminate the potential for there being, they're often like where two roof pitches meet, or there's a funny hip rafter, or some conglomeration of
right.
something that spray foam wand just can't get all the way around the back side of it. And it doesn't take but one or two of those. Again, if there's no venting above, that's going to be something that in 3 or 5 or maybe 15 years is going to have rotted that roof right out, from underneath. So that can help.
Oh.
Certainly, any layer you get under that spray foam that further reduces the amount of moisture that gets up in there is going to help. But it's got to be better than the spray foam itself, or at least it has to address the places where the spray foam doesn't, and that can be hard to do sometimes. And again, back to the eliminating moisture sources in the first place, because I have seen a lot of buildings that should have had trouble, or maybe are likely candidates for having these kinds of problems, but they're really not an overly moist building in the first place. And like, yes, we do create a lot by breathing and cooking, etc. But if there's a bath fan and it's not a dirt basement, and it's generally kept at, 45% humidity in the winter, maybe it's just not going to be that bad. So it's this whole, it makes for these really, really long answers because it's just like gray area after gray area. But yeah, you're totally on the right page with the physics of it all. Yep.
Thank you very much.
Absolutely. See Richard's still up, but Joanna, if you have any others of, go for it.
Nope.
All right. So, Nate, you may have just answered pretty much my question, which was a very simple. Is there an ideal indoor relative humidity?
Yeah, it is so subjective. The first answer is yes, it's the one that feels comfortable, right? Like that's where we have to start. And to some people, 34% might feel okay. And in that case, I guess the short answer is the driest one that feels comfortable.
Yeah, because you just threw out the 45% off
Yeah.
the top of your head.
Yep.
And
I
that's
have
kind of what I've heard too.
totally. And that's sort of a sweet spot. It's a little, and again, that like 40 to 60, and 60 might even be getting a little bit high, but I think 40 to 60 is, if you were to walk into most houses in the winter in New England, they'd be somewhere in that range. People who are extra dry or really conscious of it might be under 40, and places that are starting to run into trouble might be over 60. But it's going to be somewhere in there, and anywhere in there, generally speaking, is fine. The drier you can feel okay with, the better from a building science point of view. So yeah, 45, sure.
Yeah, because I've been shooting for 40.
Yep. I think actually, I'm always on the lookout for what are the questions for which 42 is the answer. This goes back to the Hitchhiker's Guide to the Galaxy. I don't know if anybody's a fan of that book series, but the main character finds out that the ultimate answer of the universe is indeed 42, but
Okay.
finding out the question
There it is.
is the really hard part. So you may have just found the question.
Great.
All right, good. More questions. Are those hands still raised or newly raised?
Yes. Yes. So
Yeah.
H.E. Platt is a new question, and then Kate, and then Deborah.
Great.
I have a quick question about basement and moisture in a basement. When we first moved into our house 36 years ago and found water coming in through hydrostatic pressure in the spring, a coworker said, well, only flatlanders complain about water in their basement. And I thought, well, that can't be right. So anyway, once I fixed the sump pump at the correct depth, haven't had a major problem with that. Also, moving snow away from the house, the perimeter of the house helps too. But I'm wondering, what do you think about putting some kind of coating over the poured concrete to help with moisture in the basement? Would that solve any purpose?
And you're talking about on the inside of it, on the interior?
Right on the floor, yes.
On the inside of the basement.
On the inside, the poured concrete floor.
Potentially the water that's coming in probably isn't really due to essentially what, moisture that is quote unquote moving through the concrete, like diffusing through the concrete. It is certainly possible for concrete to be saturated, in which case, yeah, it would be evaporating inside, but more likely it's a couple of spots that are actually allowing literally bulk water in. A corner or a crack or a post that goes down through. And you may know, and feel free to speak up if you do, if that's the case. If like, yeah, there's always one wet corner or there's a stream sort of in this corner or whatever it be. Um, any waterproofing that was done, most likely that would be the good effect would come from it having happened to plug or cover like a crack. That being said,
I, yeah,
yeah, go ahead.
I think the ultimate would be to do some better grading around the house, just to make sure the water flows
Totally. And what I
the
was just
way.
about to say is it's hydrostatic pressure is no joke. It is crazy. I mean, even and what hydrostatic pressure is essentially is like if you have a column of 1 inch of water in a tube, it's the amount of pressure that is exerted sideways, literally by the weight of the water pressing, outward. It's trying to get out of the tube. Um, if you have, for example, groundwater level where the ground gets saturated up, say to the basement floor or above it, and literally you're getting, as it were, like a column of water that's pushing in. It's very, very hard to seal against that, especially from the inside. And it's likely that anything you put on would just sort of get blown off. I mean, there's like hydraulic cement, which goes into the cracks and really kind of gets there. But the much better way to address it is exactly as you say, try to get it so that the water table never gets up above the basement level. And then you're back to you're still dealing with vapor. You're dealing with everything else I was talking about, dirt floors, but that's a lot different than actual liquid water. That's like water on a grander scale entering in. And so, yeah, draining away. I mean, if you're going to lengths, an amazing thing to do is to dig around down to the bottom of the entire foundation to the footings and waterproof it on the outside. Um, it's much easier to waterproof on the outside because the hydrostatic pressure is still there, but it's pushing the waterproofing up against the concrete instead of trying to push it away from. And so it's a big difference. So that alone can go a long way, but it's obviously a huge undertaking, but it could be done in concert with perimeter drains, daylighting, that kind of thing. So yeah, trying to get at it from the exterior is probably better. The other thing to say is that one way to treat basements is, and it's done all the time, is literally to just align it with plastic on the inside. And in that case, you're not necessarily trying to keep the water from getting to the concrete, you're just not allowing it to get into the airspace. Like it can sort of run over the surface of the concrete or whatever it does, or the dirt floor, but you've got this like plastic tub. But it has to be very continuous. It has to be fully sealed up around the edges and sides. And that's, potentially sort of a whole different way to go about it.
Okay, just one quick additional one. In the winter, when it's really cold and you hear the roof cracking, is that because of moisture in the wood?
It's like
Ooh,
banging.
great question.
It's really loud.
Yeah.
And it's not a lot. It's not a lot, but I've always wondered, I thought, since you know so much about water, that I
Yep.
thought, well, is it water? Is that what's going on? And we're the ones with we have a ridge vent, we have what are the soffit vent, and
Half
we also have the
gables.
huh?
The gables.
The gable vent.
Yep.
So I don't know it would be water because I don't know how there could be any water up there. But anyway,
Yeah, I
I
doubt it.
just
I
wondered.
think most likely what it is as things get cold, they shrink and they shrink differentially. So like the is it a metal roof or what kind of roof is it?
No,
No,
no.
asphalt and
Asphalt.
shingles.
Yeah. Yeah, it could be like different parts of the frame finally getting cold enough to where they shrink such that they actually move away from another part of the frame, and all that tension finally goes pop, and it's just literally wood.
Yeah,
Wood
that's how it
against
does. It's
wood.
like a pop.
Yeah, I
Okay.
mean, I'm familiar from sugaring. I'm familiar, and just being in the woods in general. There's the trees will pop when it gets incredibly cold, but that is
Oh,
actually the sap expanding and the
Hmm.
freezing, the expanding, freezing, getting um, to the point where it's actually splitting the trees open. So
ooh,
that's different because they
okay.
have they're like that's living tissue. It's filled with water. There shouldn't ever be enough water in the wood, basically ever in your house, that it's what you're actually hearing is like water freezing and expanding. I think it's more about just things cooling differentially and kind of creaking as they move, is my
Okay,
guess.
great. Thank you.
Absolutely. Kate, yeah, go ahead.
I'm gonna have an A and a B, and if it's important, just choose one.
Okay.
The last question was great. It reminded me, we've recently purchased a home built in the late 90s. The basement has what they called a water, vapor, oh, I'm sorry, I don't know what they called it, but what it is styrofoam up against the cement, wall.
Hmm.
And you can tell I barely understand it, but I want to run that by you for anything we should watch for. Um, if that's a good thing or a bad thing. And I do understand that the fire department knows it's the wrong kind of styrofoam. So if we ever had a fire, it would be toxic. But that's interesting. But B is to ask you, with this interesting brand new first climate that we're running into and the extreme heat. Um, if you could touch on anything we should be aware of with increasing summer extreme heat.
Yeah, that's a great one. Well, the most pertinent one I think is it's a combo of the increasing heat and also the fact that we have a lot of heat pumps in our buildings now, which also happen to provide air conditioning. And so knowing what we know about the mechanics of condensation, warm, moist air meets a cold condensing surface, in that we're almost always traditionally in the Northeast talking about that from the point of view of the warm, moist air being inside in the winter and the cold being outside. Well, if it's 90 degrees outside and 70% relative humidity, and you have a heat pump inside your house keeping it at 68 and 60% relative humidity, up in the roof system, you have warm, moist air from outside coming against into contact with these cold condensing surfaces on the inside. And until this point, all of our guarding against vapor drive and condensation has been thinking it was going to be going the other way. And so for example, I have a friend, who has like as many people do, has a tongue and groove beadboard vaulted ceiling in a bedroom. It's very leaky. It leaks a lot of heat, but no big whoop because it goes into a vented roof system, and so the heat and the moisture just make their way out. Well, and they got an air conditioner. They got a heat pump. Brought it down to 64 on one of those horribly hot summer days in that bedroom, and all of that warm, moist air, which comes in through the freely vented attic, comes into contact with the top side of these tongue and groove boards, which are at 64 degrees and is immediately below its dew point. And so they had rain dripping down into the bedroom through the tongue and groove ceiling because it's the exact same physics. It's just in the whole opposite direction. So that I think is probably, at least sort of certainly in the context of this whole conversation, the most pertinent change. We're going from what we would call a heating climate, where we are heating our homes, to being a heating and cooling climate, where we're also cooling our homes, and then all the vapor drive and all the condensation issues go in the opposite direction. So there's that. That's fun. Um, I think the wildfire danger and the vented roofs, that's another example of how sort of climate induced changes are changing the way we're thinking about building science yet again, for a whole new host of reasons. Um, yeah. one, not to go too far off on a tangent, but it was really helpful for me at some point knowing what we've been talking about the mechanics of condensation, and just simply like warmer air can hold more water. And it's like, oh, well, what if you apply that on a global scale? Even just a little bit, like maybe just the whole atmosphere just gets a half a degree warmer. Like that's probably a lot more water in the sky ready to come out when things get cold enough. Like it just made me understand at a very simple level, like, yeah, make the air warmer, you get more water in there, the whole system just gets more dynamically active. And like that's it. That's all that's happening. It's the exact same fundamental physics as we've been talking about right here. It's just implemented on a massive scale. Deborah, yeah. Hopefully, Kate, hopefully that was helpful.
It was awesome. I'm trying to let the next person have a chance.
Okay, and then I'll if there's a minute, I'll come back to your part A too. But
Um,
Deborah, go ahead, please.
yeah, I kind of have A and B. My A is that blue sheetrock board. Does that actually do anything? Is that um
Yeah, and you mean
part
the stuff
way?
that's like likely to be installed in a bathroom, that's sort of
Yeah,
greenish bluish,
yeah.
yeah. The only difference about that stuff, as far as I understand, is it has some sort of additive that is mold resistant.
Okay.
It doesn't actually perform any differently in terms of permeability or water, waterproofness or anything like that. It's basically they're like, oh, this stuff's probably going to get damp, so let's put some fungicide on it. That's all that is.
Okay.
Yep.
All right. So it's not any barrier of any kind. All right.
No, although watch out because now you're using words that mean things to me. Sheetrock is a great air barrier. And like this, not to get too far into it, but to go back to the whole conversation about, spray foam in between rafters, and is there anything to be put under them like a Siga or an Intello or something? Taped and mudded sheetrock is a perfectly good air barrier. It is somewhat vapor permeable, although that doesn't really matter. The problem is that it's usually not fully continuous and, isn't exactly in the right places. But anyway, just, yeah.
Yeah, so I have my bathroom upstairs that has the usual shower, and my builder when I built was in the late 80s, a very energy conscious builder. I have 10-inch walls and everything. He did not want to install a bathroom vent. He just told me to just be sure I opened the windows when I took a shower. So I've never installed a vent in my bathroom. I have that blue board. I have by now several layers of latex paint over the sheetrock, but should I consider installing a vent up there, or am I fine the way it is?
I would. I mean, he's right. Like a window opened to the correct degree at the correct time and closed again is a perfectly good vent. If only we could all expect perfect diligence on our own part about operating the windows. Yeah, generally speaking, it's a really good idea to have a vent, especially in a bathroom, because it's sort of the biggest point source of moisture in the house, during a bath or a shower. Like there's just a lot of moisture, um, and it's going to be trying to get out somehow. Um, and yeah, it may be that it's working really well, and you've been diligent with the window, and it's been able to exhaust most of it. It may also be that there's actually a fair amount of, maybe not horrible, but kind of hidden damage or hidden trouble
That's
above the
yeah.
ceiling there.
Okay, that's kind of what I was
Yeah,
wondering, if there's a surprise for me waiting
it
for me or
it
something.
matters a lot whether or not it's a vented roof above it, whether it's like a vented attic. Do you know that?
Yeah, that was my my earlier question about the,
Yes.
I have blown in like 5 feet of insulation. So, there's not, the moisture is probably not getting through that. It's got a plastic um, barrier between the sheetrock and the insulation.
Mm-hmm.
Um,
Got
so,
it. Yeah, short answer is almost always going to be, yeah, put a bath fan in the bathroom. It's never going to hurt, and it's certainly going to help.
okay. And my second kind of comment thing is I built my house in, I think, 86, 87. And when I first moved in, the condensation on the windows was like crazy.
Mhm.
And now, right now in my kitchen, it's 34% humidity. And so I'm wondering, over time, wood dries more and more and more. And I have hardwood floors and wood cabinets and all that. So over time, does does the house get to a equilibrium point and the moisture? I mean, it seems like my house is rarely humid, so
Mhm.
I'm not sure
Um,
what's helping or hurting, or whether it's just time and would dry, all the materials of the house dried out, and now I'm in a dried out state, or what.
right. Yeah, great question. Yeah, it can take up to 2, maybe 3, more like 1 to 2 years for new framing lumber or new wood to dry out. But after a couple years, it's generally usually achieved sort of that 8 to 12% wood moisture content that I think I mentioned earlier. And that it'll vary seasonally. It'll go up and down a little bit, but it's basically in a state of equilibrium. And the real driving factors around keeping the house dry at that point are going to be around ventilation, and controlling the other sources of moisture. The wood will basically just kind of settle into being, equal to the environmental conditions.
Okay, yeah, that makes sense.
Yep.
So we have 5 minutes left, so maybe um, we could go to Julie's question, and then there is a question in the chat if we have time.
Okay.
I'm sorry, Kate, if that's okay, if we skip over you.
Absolutely fine.
Yeah, Julie, go ahead.
Oh, hi. Thank you. This is a great presentation. My question is, could you go into a little more detail about heat pumps and the good aspects and those that need to be considered? I have a heat pump in my home and really like it. But I'd like to know more about the disadvantages and advantages of the heat pump and circulating air.
Yep, absolutely. Yeah, try to run through it as quickly as I can. Yeah, so the number one advantage, as I'm sure you understand, is they're 3 to 3.5 times as efficient as any other use of energy that we have. And we won't get into it all does come down to the mechanics of condensation and evaporation, and there's some energetic magic that goes on in what's called the phase change between liquid and gas, but we're not going to get into that. But anyway, they can essentially take 1 unit of energy in and give you 3 out, whereas anything else we have struggles to get to a 1-to-1 ratio. So they're just incredibly efficient. That said, a few things about them. One, yeah, there's this sort of hidden potential problem where we're going to also use them for air conditioning and therefore drive condensation in the other direction. That's out there, not necessarily a big concern. Um, there is a lot around the mechanics of heat transfer and what feels good to a human body versus what is just quote unquote a certain temperature, which is to say, some people find, and you may not, that a heat pump which gives you an even 70 degrees, and sure, it's 70-degree air, really just doesn't help you get warm the same way, for example, a wood stove or a radiator, which you can moderate. You can feel 60 degrees when you're farther from it, or you can get really close to it to where you're feeling 90 degrees on your skin, and it's a much warmer radiating body. So just sort of from a felt comfort perspective, sometimes people are like, boy, I have the heat pumps going, but it just never feels warm. So that's a subjective thing. Um, I think probably one of the biggest concerns that I see with them is just maintenance. Like they need to be maintained. They need to be cleaned regularly. Not only the where the air is circling through, which certainly does, those filters get clogged up, but also the drain, the condensate drain lines. And if either of those get plugged, they just really struggle, and can even be sort of reintroducing like mold, like if you have a moldy one. So that maintenance is a thing, but generally speaking, no, they do what they do very, very efficiently. And they make use of a kind of a magic around phase change.
Right. Okay. Well, thank you. That's helpful.
Yeah.
Maintenance is really important
Yep.
in terms of cleaning the filters, but also, like you said, the condensate
Yep.
line and actually cleaning inside in the fins and everything like that.
Yep.
Regularly
Exactly.
in dogs, which I have, that adds to the filtration challenges. So cleaning those filters, it's all real important. Thank you, Nate. Great.
For sure. Yeah, and just real briefly thinking about it too, like when they're used for air conditioning, that means that the surfaces right there at the heat pump are quite cold. But they are cycling through this warm, fairly moist air as they do so. So they're a magnet spot for summertime condensation. Yeah, for sure. Yep.
Great. Thank you so much.
You bet.
So Nate, before we go maybe to this last question, I want to ask, are you willing to uh, share your slides with the audience?
Yes.
Oh,
Yep.
wonderful.
Absolutely. Yeah. I think, right. You had asked me to do that. I didn't have them done until about 5 minutes before I started. So
Oh, no problem.
but
And I will be letting people know when the recording is ready.
yep.
So, okay. Are you willing to take one more question?
Sure. Yeah,
Okay,
absolutely.
from the chat, from Nancy Whiteman, is there a heat pump type system to install in bathrooms to recover heat and remove moisture from wet bathrooms?
Um, uh, let's see, Nancy. Yeah, I see you there. So when you say heat pump, do you mean literally like a heat pump, as we call them now, these condensing units? Oops, let's see if Nancy can join in. I sort of have some questions about the question. Um, let's see. So, well, actually, let me think through this. I mean, yes, there is such a system. A couple things. When we're talking about capturing heat, as it were, like as we exhaust air, that is what an ERV or HRV does. That's sort of exactly what their magic, quote unquote, is that they have the incoming air and the outgoing air, and they literally, like, if you open up an ERV, there's this honeycomb structure where the two air channels, they go right by one another and they exchange heat, but they don't mix. And it's an attempt at warming up some of the cold incoming air with the heat from the outgoing exhaust air. And so in many new like high performance homes, yeah, the bath exhaust may be built directly into the larger ERV system or HRV system. And so in that case, yes, the what is being extracted from the bathroom is not only exhausting the moisture, it's also recapturing some of the heat. It's doing that everywhere throughout the house, so it's not exactly bathroom specific. Um, Most of the other, like for example, like bath exhaust fans, which may be more what you're getting at, don't necessarily have. I don't know of any examples that it's like an exhaust fan with a heat capture thing, because essentially you'd sort of be reinventing the HRV or the whole ERV system. Um, they're more like the quote unquote just bath fans that we're talking about are just, yeah, they're exhausting a bunch of air and a ton of moisture at the same time. And the general thought is it's worth it to lose a little bit more heat in that moment because you're getting rid of a huge point source of moisture, for 20 minutes after a shower or whatever. So it's worth it to lose the heat.
Okay. getting a lot of very positive comments in the chat.
Oh, good.
Really,
Great.
really appreciate this amazing presentation. And I learned a tremendous amount.
Wonderful. Glad to hear that.
So thank you, Nate, very, very
Absolutely. I
much.
appreciate the attention and all the questions. That really lets me know you guys are listening. So appreciate that.
All right. Well, enjoy Georgia if you can.
Will do.
And thank you.
You got it. So long, y'all.
Good night, everybody.